Hey everybody, I wanted to show you a couple of standing waves here. So you can make a bunch of different standing waves for any given situation. Let me just show you a few, and then we'll talk about some of the properties they have and what special characteristics they have to have in order to make a standing wave. So the simplest one, or the longest wave we can make, looks like this. You have just one area in the middle that's doing a whole bunch of moving, and then the ends are pretty much still. The next simplest, or the next longest wave, will look like this. Here we have two areas in the middle that are doing a lot of moving. Also an area in the middle that isn't doing any moving at all. And then the two parts at the end that aren't moving at all. The next one will look like this. Oops. There it is. Three areas in the middle doing lots of moving. Two parts in the middle that aren't moving at all, and then the two ends aren't moving at all. And I think I can do one more here. Four areas in the middle doing a lot of moving, three areas in the middle not moving at all, and then the two areas at the end not moving at all. I sketched out some of the waves that we saw. Now, there are only certain waves that will work, that will make standing waves here, because the way that I had that set up, this end over here and this end were pretty well fixed in place. Maybe a little movement there, but for the most part, they had to be still. And so only waves that would let those spots be still could exist. So one wave had those two spots still, and then just one spot in the middle that was doing a lot of moving. The next wave had those two spots still, and then an extra spot in the middle that was still, and then these two areas moving a lot. And then we kind of added to that. So here we had three areas that were moving a lot, two that were still, and then the two ends that were still as well. And then the last one we saw, we had four areas that were moving a lot, three areas in the middle that were still, and then the outsides, again, were still. So these were the waves that fit with the situation, that fit with that slinky. And so we can learn a little bit more about what conditions we have to produce a standing wave by thinking about what the wavelength would be and how that relates to this distance. So I'm just going to label this distance, the total length from where I was holding it to where the chair was holding the other end. We'll call that a distance L. Now, that spring moves back and forth so fast that it ends up kind of just looking like a blur. But we understand that at any moment in time, the spring can only be at one position. So maybe at one moment it was at this position, and then some time later it was at this position. And then in between it would have been at the spots in between there. And down here we can do the same thing. So at one moment maybe it was down like this, and then it would have gone up like this, and then down, and then some moment later would have gone up first and then down. So we start to see the wave shapes here. We see the wave curves in each of these. Up, down, up, back to the middle, and then the same thing down here, but in reverse. And then one more time, up, down, up, down, up, and down, up, down, up, down. So we can then think about the wavelength for each of these situations and how it compares to L. So in this one, I see that I've got a bump up, but my wave, the next thing it's going to do is come back down. And so this isn't a whole wave. In fact, if I look at this one that has a bump up and a bump down, I can see that the bump up, that's only half of this complete wave. So here I could say that the length of this spring, the distance from where I was holding it to where it was anchored on the other side, L would be equal just 1/2 of a wavelength. Down here, we've got one complete wave, an up part and a down part in this same distance L. So L is equal to lambda, the wavelength. Down here I see I've got one complete wave here and then an extra half of a wave. So I only need from here to here for my, my one complete wave. Now I can think of this string, this distance L, as being divided into thirds in this picture, and two of those make up one complete wave. So from here to here is one complete wave. So that means that the length of the string, or of that distance, must be 1.5 or 3/2 times the wavelength. And then down here I've got one complete wave there, another complete wave there. So here our length is enough to fit two wavelengths, two lambdas. Now you might also write this as 2/2 times the wavelength, or this as 4/2 times the wavelength. Pardon the announcements that are going on here. When we do that, we can see that if our length is some multiple of 1/2 wavelength, so 1/2 wavelength, 2/2 of the wavelength, 3/2 of the wavelength, 4/2 of the wavelength. If that's the case, so if L is equal to a multiple of 1/2 of a wavelength, then a standing wave can be created. And if it's not a multiple of 1/2 wavelength, say it's 2/3 of a wavelength, then we can't make a standing wave with that wave. We'd need a different frequency, a different wavelength to make it work with that situation. That's all for standing waves we'll do right now. We're going to come back to standing waves, though, when we talk about sound and music, because musical instruments create standing waves. So we'll do a lot more with the frequency of the waves at that point, and how we can alter the notes by doing things like changing the length of the instrument, or maybe the tension in a string to adjust wave speed. All this stuff with standing waves is going to come back to us when we study sound in our next unit.